third tutorial, part 1. Parts 1 and 2 are independent of each other. Part 3 depends on both of them. In part 1, we will talk about the types of higher order functions. Higher order functions are functions that return functions or that take functions as arguments. A very interesting thing happens when you consider functions that return a function. Here's an example. The function log_width takes a string argument, which is not itself a function. So that's just a normal argument, non-function. But it returns the type, which is a function. So it returns a value of type function from string to unit. Why would we want to use such a function? Well, for example, we want a logger function. We want something that prints logging statements. And we want to prepare this logger so that whatever statement it prints, before that statement, it also writes the topic of the statement. Let's say some topic such as result or intermediate or something like this. To prepare this function, we give it topic, and then we return an expression which is itself a function. The function takes some argument x and prints a string which is topic colon x. So then in the code we will say something like this. A status logger is a function from string to unit. Well, it's just going from string to unit because println returns unit. It does not return any useful value. This is just an example. So status logger is a function from string to unit which we obtain by calling log_width on the string argument result status. And the result will be that status logger will be a function that prints, let's say, success, but before success it prints result status. So this is a mistake actually. This should be status logger, not primary logger. I will fix that in the slides. So this must be primary, not primary logger, but status logger for this code to work. So the result is that status logger called on success will print result status, which is the topic, colon success. And we can call the same function in a syntax that is in one line. So you see here we first made this call, which returns this value, and then we call that same value, sorry about this error, we call that same value on the success. And we can do the same, since these are all values, by first doing this, first calling this function, getting the result, which is a logging function, and then calling this logging function on the success argument. Let's see how this works in interactive Scala mode. So we define a function which takes topic of type string and returns, let's say, string to unit, as we decided. And that is going to be x going to println topic x. So we evaluate this, and then we say val status logger equals log with result status. And then we say status logger of success. So let's see now. Okay, so we got a printed value, result status equals success. So the same thing can be done if we call log with result status success. So yeah, same thing. So you see what happens here is that the function log with, when called on this argument, returns a function, which is this expression. So we're using expressions that are anonymous functions. We could have a syntax that is like this. As well, just to be, oops, I have done something. Let me do this. Right. So the syntax could be like this. It's exactly the same result. So log with returns this expression, which is itself a function. That function takes some x and prints this message, which is topic x. And topic was already given as the argument here. So here we put in the topic right in this function that we return. So when we say status logger, log with result status, the result status is already in that status logger inside this expression. So when we say status logger success, it prints result status success. And exactly the same is happening when we do this. So first we do this, log with of result status. That returns a function, and that function can be called on its argument, which is success. So that results in the syntax that looks a little odd, maybe, which is a function with two pairs of parentheses. That syntax is what I'm going to talk about next. This syntax is actually very important in functional programming because we can write it in a much shorter way, namely like this. Why is that? Well, you see, there are two ways of defining functions in Scala in terms of syntax. One way is to define def, to write def, and then function name, and then in parentheses to write arguments. The other way is to say val, or let's say val, and then the type, say that the type of this val is a function, and then equals, so we still have equals here, but it's going to be a function expression. So here it's not so obvious what the type is of log with, because log with actually has two sets of arguments. One, which you can see here, log with is a function that looks like it has two sets of arguments. The first set of argument here in the first pair of parentheses, and the second set of arguments here in the second pair of parentheses. So an alternative syntax for that is to write, let me show you how to write that. So I would say val log with, let's call this log with 1, just to make it a different name. And the type of that, I'm going to show you different ways of putting types in it, but let's say I want to have a function that takes a topic and returns this. So we can do this, right? So we take a function which was returned here, and we say that function is returned when we give topic as argument. So now, if we use this syntax, IntelliJ is unhappy because it wants parameter types. So you need to specify types. There are two ways of doing this. I mean, this would not compile. It's not just IntelliJ that's not happy. You need to specify types. So in Scala, you need to specify types in quite a few situations, although not everywhere. So we will go through this more slowly. So what is the parameter type? Well, the syntax for parameters is that you put parentheses and you say type. Let's say this is string. So now it's happy about this, but it's not happy about this x. So let's put a parameter type in here as well. Now it's completely happy. And now log with 1, the type is string to unit. Now you see it put parentheses here, which is kind of more clear maybe. So we take log with 1 is a function that takes a string and returns this, which is itself a function that takes a string and returns unit. Now, there is a syntax convention where the second pair of parentheses, this last one, can be omitted. So let me show you how to do that. I call this log with 2, and I specify the type string, string unit. And then I say topic, and then I do the same as I did here. Topic returns this value. Okay, it's happy. There are no red. Actually, it tells me there are unnecessary parentheses. So this is the syntax convention I'm talking about. The second the second pair of types don't need parentheses around them. So neither here I need parentheses around these two. Although IntelliJ will not mind if I put them here, but they're not necessary. It's exactly the same thing. This is the syntax convention. Basically, the syntax convention is that this syntax, XYZ, means this. The parentheses are implied on the last pair, not on the first one. Now, what would be the first type? Let me write this as a comment. So what is string to string to unit? What would that mean? That would be a function that takes a string to string function as the first argument, or the only argument, and returns unit. So that would be also a higher order function, but that function does not return a function, it returns unit. Its argument is a function. That's a difference, right? The function that is an argument or a function that is a return value. So here we have a function whose return value is a function. Here I'm writing a type of a function whose argument is a function. In this case, you need parentheses around the first pair. In the second case, you don't. So this, you don't need the parentheses around these two. This is not necessary. So this is the syntax convention I'm talking about. The reason for this syntax convention is what we just saw. the natural way in which we call a function that returns a function is that we want to write things like this. We want to call the function with an argument that returns a function. We want to call that function again with some other argument, just like we did in this example. We say status logger equals this, and we call status logger of success. So we should be able to replace, when we write status logger of success, we should be able to replace status logger with this expression. Right, so status logger is equal to this. So we can replace status logger here with what it's equal to. It would be very convenient if we didn't need to write parentheses like this again. So these parentheses are unnecessary, as IntelliJ tells me. So that's the convention. So because we don't write these parentheses, but that is natural because of this replacement of the expression. Right, so I can write this or I can write this. These expressions are equal since I defined status logger to be that other thing. Because of the natural way in which we write this, naturally the type of this must be a function, which is this. And so we don't want to write extra parentheses here either, since we don't write them here. So if we did the opposite convention here, then we would have to write parentheses like this all the time. And that's not going to be, well, that's not going to bring us any advantage. So these two syntactic conventions go hand in hand for the reason I just described. It's very natural not to write extra parentheses here, and once we do that, the type of f is actually this, and we don't want to write extra parentheses in that type either. So this syntax is called Curried. I put here a link to the Wikipedia page. If you want to write about why this is called like this, this is in honor of a mathematician whose name was Curried. Now, having understood how we write the syntax for higher order functions, let's do something with the types of the functions. To understand what we do in functional programming, let's contrast two different kinds of functions. And I selected this example of two functions. The first function, the hypotenuse, is a calculation of the Pythagoras theorem. So you take x and y as two arguments, and you return the length of the diagonal of a rectangle with sides x and y. Now, note again the syntax. I'd like to call your attention to the syntax in Scala. This is a little quirky. This function actually has two arguments. This is like a tuple, but it is actually not a tuple. So in Scala there is a difference between a function that takes two arguments, like this one, and a function that takes a tuple as its one argument. In other words, a function with one argument whose type, the type of that argument being a tuple of two elements. The difference in the syntax is extra parentheses. So the next example, called swap, is a function that takes a tuple as its only argument and returns a tuple also. So this is a type expression, which means we take a tuple and we return a tuple. An extra pair of parentheses is necessary on the left, but it is not necessary on the right. This is because of Scala's special feature that it distinguishes between two different function types. So we could rewrite the first function as a function that takes a tuple of two doubles, and then I would have to put extra parentheses here, and then I would have to do pattern matching on the tuple on the right hand side, which would make the code a little longer. But it would be possible. Just a little extra writing. So in Scala, usually arguments of functions are not tuples. It's not usually necessary, but sometimes it is, and then we do this. So swap is an example. It takes a tuple of two doubles and returns again a tuple of two doubles, and in that tuple the order of two numbers is reversed. That's a very simple function. Now, the interesting thing about this function is that it doesn't actually use the fact that its arguments have type double. All that function does is exchange the order of these two arguments. So in principle, this function could, with the same code, this code remains the same, it could work on a tuple of any type. Let's say a tuple of types x and y. And in order to write this in Scala, we parameterize the argument types. So the syntax looks like this. We introduce type parameters in square brackets, and once we introduce them, we use them in the type annotation for this function. Type annotation is whatever you write after the colon. So this is a type annotation. In the type annotation, and also on the right hand side, if you want, you can use x and y as if they are defined, but actually these are type parameters. So this function can work with any two different types, x and y. They could be the same, or they could be different. Right now there's no specification about them. There's just two different type variables, x and y. So you see, the code of the function is exactly the same as we had here. So we just kept the same code, we just changed the type of this function, and we made it very general. So this is what I would call a function with fully parametric type. In other words, this function doesn't have any type in its signature that is not a type parameter. It doesn't use any specific types like doubles, integers, booleans. It only uses type parameters and no information about what these types are. So this is a fully parametric function by my definition. Now, notice that the first function, the hypotenuse, cannot be generalized in this way. The first function is very specific in what it does, and so this kind of calculation makes no sense, for instance, for string arguments or Boolean arguments or even integer arguments, because you cannot very meaningfully extract square root from integers. I mean, you can do it in a very rough approximation. So we cannot easily make this function work, let's say, for string and Boolean instead of double and double. But this function we can. So the first function cannot be very usefully generalized. It's too specific in what it does. But the second function can be generalized. So there's one little quirk, a detail or about Scala. Notice we could previously write this as a val. So this we could say def swap or we could say val swap, because this is just a function. It is defined by a function expression on the right hand side. So we could say val hypotenuse or val swap. But here we cannot say val. We must say def. This is so because Scala does not actually support vals with type parameters. This is a limitation of the language. In practice, this is not very serious. You just use def. There are other ways of going over this limitation, which is to use type parametric classes or traits. I'm not going to talk about this right now, but later we will see classes and traits with type parameters. Inside these classes and traits, you can define vals, and then these vals could have types involving the type parameters. But you cannot say, for example, val swap of x, y. That just doesn't work like this. So in this tutorial, we're just going to use def. But think about this as a val or as a value. It's important that we think about functions as values. And so it's emphasized that this is a value, because although it's a def, there are no arguments, so it's basically like a val. It has a type, so it's like val blah colon blah equals expression. So we are going to think about these as values with this type equal to this expression. Just like val x colon int equals 5, def id colon this equals this. So we think about functions as values. Here are more examples. Id is a function that takes x of type t and returns the same x. Not a very interesting function, perhaps, but it's quite useful in certain cases. Const is another interesting function. It has two type parameters, c and x, and the type of this function, I put this in parentheses here just for clarity, like this and like this, but in actual code you don't need these parentheses if you don't like them. Just to make clear visually that this is the type of this, and these are the type parameters. So what is this? Is a function that takes a value of type c and returns a function that takes a value of type x and returns a value of type c. How does it work? Well, it takes a c, and then it takes an x, and then it returns that c. So the x is ignored. That's how it works. Okay, well, this function may seem to be very strange. It takes an argument, it ignores that, and returns the first argument. But this is actually also quite an interesting and useful function. Final example on this slide. Compose is a function that takes two functions as arguments and returns a function which is their composition. We have seen this in a previous tutorial, perhaps, but let me write a full general form of it. So it has three type parameters, x, y, z. The first parameter, the first argument of compose is a function that goes from x to y, and the second argument is a function that goes from y to z, and the result is a function that goes from x to z. And then the code of this function is very simple. It's this expression, very short. It takes argument x of type x and returns g of f of x. So f of x will have type y, g of f of x will have type z. I would like to emphasize that the Scala compiler will not allow you to use these types incorrectly. These type parameters are going to be checked by the Scala compiler. Let me show how that works. So I define this compose function, and suppose I wanted to, well, suppose I made a mistake here. I did f of g instead of g of f. There is a mistake, and IntelliJ shows me that in red. Actually, this also will not compile. It's not just IntelliJ. This will not compile. Expression of type y does not conform to expected type z. So g of x is a function that takes y and returns z. I did not say what type x was, but actually it doesn't matter. So g always returns z. F always returns y. And I said, so whatever the argument of f is, it will return y. But I said that the function returns z. So it says expression of type y doesn't conform to expected type z. So z was specified as the return type, so it's expected z, but I did not give you an expression of type z as a result. Let's correct this error and test that this works. To test, we will define two functions. Let's say a function going from integer to Boolean, and the function going from Boolean to string. We'll compose them and get a function going from integer to string. So let's say first function is going to be from int to Boolean. It's just going to be x going to whether x is even. So x remainder in division by 2 is 0. And b will be a function from Boolean to string. It's just going to be printing the Boolean, let's say. I forgot the syntax. B is going to be to string. All right. So now let's say C equals compose A, B. Now, what type is C? Let's press Ctrl-Shift-P, which is in IntelliJ, and it tells me it's from int to string. So that's fine. Let me compute C of 12. So the string true, and let me compute C of 11. And that's false. So these are my working examples. Now suppose I made a mistake here. I said compose BA. What would happen? Right away, I've got red here. But actually, we see here an interesting thing. IntelliJ does not show you the error correctly. If I press this button, I get a different error. It does not show me here red, but actually it's a type mismatch. So this code actually won't compile on line 6. Line 8 and 9 also have a type mismatch, but actually line 6 doesn't compile because the functions have the wrong types. B and A must be composed in this order. Similarly, if I made a mistake here and I said g of x, not just g of f of x, then if I compile this, there's a type mismatch. So just to warn you that IntelliJ doesn't always show red in your editing window, but actually the Scala compiler will not allow you to compile code that is having a type mismatch of any kind. So the correct code would be g of f of x. Then you get the result here. So actually, this button will then run, and this was just a digression to show you that the Scala compiler will strictly check all the types that you specify and will prevent many errors happening by oversight if you put functions in the incorrect order when you compose them or something like this. So at first it could appear that these functions like this, taking x and returning x again, or this, are pretty useless. This is not so. We will see later that these functions are building blocks in several ways of interesting programs, but for now these are just examples of function types. Let us go through some more worked examples. All of these examples are implemented as tests in the test code here. So here are the hypotenuse examples, the swap example. There's some more examples here with a const, using the const, and using compose. You can use compose inline like this. So you do inline two functions like that, function expressions, and the result is a function of this type. And one interesting thing is that you don't necessarily need to specify the type. If I delete this type here and I press Ctrl-Shift-P, the IntelliJ then shows me the type. So what's happening here? IntelliJ and the Scala compiler both, they will infer the type from the code that you write. So you write some code, you do specify some types like this, and then clearly this is a string since you're doing toString. So if you do Ctrl-Shift-P, it knows that toString, the function, returns a string. So compose has type parameters. The Scala compiler will find the values of these type parameters that fit in this case. So for example, this function, obviously you're returning a Boolean here, because this expression is a Boolean expression. So this first argument has type integer to Boolean. This is inferred from the code that you wrote. You don't have to say explicitly that this is integer to Boolean. You just say this is integer. Then it knows this must be Boolean. So it infers that this expression is integer to Boolean. And the compose function has the first argument x to y. Therefore, x, the type parameter, the capital X, must be equal to the type integer as a type variable, capital X, and the capital Y must be equal to the type Boolean. Similarly, the second argument of compose is this expression, and it has type of a function from Boolean to string, which follows from the code. So the Scala compiler then looks at your definition of the function compose and finds that G has type Y to Z. So obviously the type variable Y must be equal to the type Boolean, and the type variable Z must be equal to the type string. In the previous argument, Y was also equal to Boolean. So that fits. Y is the same Y as this. It has value Boolean, Z has value string, X has value int. If any of these types did not match, like for example the first argument gave you from integer to integer and the second from Boolean to string, then this Y must be integer, but this Y must be Boolean. That does not match. This must be the same value of the type variable. The compiler will then give you an error. In this way, the compiler infers the type that this is integer to string. And so F, if you do Control-Shift-P, it tells you it's integer to string. Another function in IntelliJ is option enter, which says add type annotation. It automatically inserts the type annotation that it inferred from your code. This is also a very useful function to check that the compiler understands your code in the same way as you think your code is supposed to be working in terms of types. So this will give you a check that the function f has the type you think it should have. But you don't, once you check that, maybe you don't need to write this type. The Scala compiler does not infer every type. It infers most, but not all types. In many cases, you have to specify some types. For example, type of argument in a function often needs to be specified. Alternatively, you could specify type arguments of the compose function. Let me show you how that works. Let's call this F1. Now I'm going to delete the type annotation here. And now once I delete them, things become red because it doesn't know that x is integer. You see, compose has a fully parametric type. So the first function is x to y. It has no clue that x you think must be integer. But if I write here, I can, with this syntax, I can say it's integer. So I have to specify these three type arguments: integer, Boolean, string. Once I do that, the Scala compiler will check that everything I wrote here fits what I just said. So what I said is that compose in this line is called with type arguments int, Boolean, string. So f must be int to Boolean, and then this fits. X is int. Let me do Control-Shift-P. So now Scala knows that this x is integer, this y is Boolean. So it knows that. Once it knows that, I can write it in a shorter format, which I showed you in the previous tutorial. This format of the functions. Typically, if you have a function that looks like x going to x something, you just replace this by underscore. This is a special syntax that Scala provides to write functions in a shorter way. And now, since all types are specified, you don't need to write type annotations in this long format. So this is a shorter format. And then f1 of 23 should equal false. f1 of 22 should equal true. Let's run this test and see that it passes. and that it compiles, of course. Even though we don't see any red, there might be errors. But the Scala compiler will catch them. Everything is green. Good. So let's look at our first worked example. I define the function's constant id, as in the previous slide. What is const of id? And what is the type of that value, const of id? So how do we find out? Well, this looks like an idle question, but it's a useful exercise. So let's reason about constant id. Constant id are defined here. So what would be const of id? Const has the first argument of type C. So when we say const of id, it means that C is the type of id. Now the type of id is t to t, is a function. It means that C must be equal to the function t to t. Let's write this as a comment. Const of id. So C const has two type parameters and id has one type parameter. So let's try to put these parameters in. So id can have any parameter t. Const must have the parameter c of x. So the first argument c must be equal to the type of id of t, which is c to t. So c must be t to t. Good. Then, when we apply const to its first argument of type c, it returns a function of type x to c, where x is anything. So it means that the result of applying const to its argument is something of type x to c. Now c, we know, is t to t. So the result is this. I don't write parentheses because by convention these parentheses are unnecessary on the right side of the arrow. So this is the type of const of id. It has still two unknown type parameters, x and t, and the type is x to t to t. So that is our reasoning. Let me go to the actual code that I prepared. So const of id. So let me put the comment here. And let's see what happens if we just start writing. I will delete this. Let's see what happens if we write code like this. Const of id. What would be the type of this? So let me press Option Enter and add type annotation. It's a very curious type. It inferred any to nothing to nothing. So it looks like x to t, except it didn't introduce type parameters. So Scala does not infer the most general type, which we inferred. Well, Scala's compiler is limited in this way. Its type inference is limited. So this is certainly not going to work. And nothing is a very useless type. In this case, we actually don't want this type, but that's what Scala infers because it has no information. Now, the second attempt I made was this. I put a type parameter here, and then I say id has that parameter here. So what the result of this is any to t. So it did not infer type parameter x. Like I said, Scala cannot really do this. It will infer nothing or any. It cannot infer that there is a type parameter. Okay, so that is a little better. Any is really any type. It's a type that fits anything. It's also not very useful. It doesn't check any correct types, so that's not great. Let's try this. So you see, we had this idea that this works when C is T to T. Let's put explicitly, let me rename this to T. So this is what we wrote, okay? So let's see if this makes IntelliJ infer the type. Yes. So let me rename this to X. And then we have exactly what I have here in the comment. So another way of achieving the same result is that I write the type here. And then I don't write any type parameters on the right-hand side. That works too. So here what happens is that I specify the type, and IntelliJ, or Scala compiler rather, will fit the types. So it knows this is T to T, this is C to X to C, and C will be equal to T to T. So until now, I only looked at types. I don't actually didn't talk about what this value does, this const of id. Well, it's a function that takes an argument of any type and returns this, which is the identity function. Let's check that it works, actually. So let me say C equals example 01b of, let's say, some number. Okay. So something is wrong here. Yes, so I define this method twice. Let's call it C. Okay. Now, the result of calling this function, which is const of id, on a number is a function which has no type, nothing to nothing. So I need to specify type parameters here. So let me say this is int and this is boolean. Then C will have type boolean to boolean. So in this way, I get an identity function of type boolean to boolean. Now this is more flexible. I can define a function which is of type t, where I say this is of type t, and then I can have a function of type t to t, right? So, and this is an identity, so I can say, for example, C of ABC. That should equal ABC. Let me run this test. So now C is the identity function. Now this identity function is fully parametric because I put all the types in here. So green. To run the test, I press Ctrl-Shift-R, by the way. Very useful thing. If you are in a test code, then you just press Ctrl-Shift-R. It only runs one test. All right, so these are the types, and this is the value. It's an identity function of some arbitrary type. Second example, define a function twice that takes a function f as its argument, returns a new function that applies f twice. For example, twice of this must return a new function which is equivalent to, adding 6. So adding 3 twice. So let's implement this function. Here's the implementation. Basically, let me remove the type. And now it's red. So the function twice takes a function f as an argument, and function f has some type. Which type should it have? Let's reason about this. So this is a solution, but let's find out how we reason about the problem to derive the solution. So let me write this as a comment. I want to do a function twice must take some f as an argument. So let's say this is a to b, and it must return some c. So what does it do? What is this c? Well, we're required to return a function. Okay, so this function should be applying f twice to some argument. So f of x. Now what is x? Well, obviously x must be the argument, so we need to return this code. So this code seems to be clear. We need to return a function that takes x and applies f twice to x. So what remains is to determine the types here. Right now I just said a, b, c because I don't know yet what they are. The code is already fixed. This is what we want. Now, what is the type of x? Well, it can be any type. So let's say that the type of x is d, for example. Well, then we need to apply f to x, and f has type a to b. The only way that can work is when x has type a, then f of x will have type b. Okay, so d actually needs to be a. Now, the result is that f of x has type b. Now we apply f to that, but f needs type a as argument. This can only work when a is the same as b. Alright, now f of a is a, so the result of this whole thing must be a. So c is not actually a different type, it's also a. Alright, so now we need an a as a parameter, just one parameter. In this way we derived the code. And actually this is a to a, not a. Sorry about that. Because we are returning a function. Right, now you see there are two ways of defining this. They are different only by syntax. One is that we say define twice, and then we specify argument in parentheses, then we specify the return type, and then we write the code. Second way is just different syntax, is to say this is a kind of a value of this type. So the first argument is this type, which is the same as this. It takes this argument and returns this. And here we could write parentheses again like that, but this is not necessary by the syntax convention. The first pair of parentheses is required, it is necessary. Okay, and what is the value of twice v? It is a function that takes this, so it takes f of this type, and returns a function that takes x of type t and returns this. So these are two not identical but equivalent ways of defining this function. Which one is more convenient? Well, the first one is less code to read, less code to write. However, the second one emphasizes the value nature of functions. So sometimes, for clarity, you would do this, but most of the time you would do this because it's shorter and also easier to read. Here's a function, its argument, its value, and its code that takes argument and so on. And you could even declare this function with the syntax with two pairs of parentheses. So let me show you how that works. So I declare the first argument, I declare the second argument, which is of type t, in the second pair of parentheses. So this is this x, which was here, which must be of type t, so I declare it here. And then the result is of type t. And then I type this as the code. Now, let's call it twice 0, so the tests don't stop working. Now, all of these three definitions declare exactly the same function, which has effectively two pairs of arguments. Two sets of arguments. The first set is this, the second set is that. So in Scala, you can have functions that have any number of sets of arguments. In this case, each set has just one argument. So now notice this is not the same as twice f t goes to t x t. That's not the same. That function is not returning a function. It just returns a value. And it has two arguments. You cannot call this function with one argument at a time. With this syntax, with two sets of arguments, you can call this function with the first set of arguments and get a function back. This is the curried syntax. This is not curried. So this is not what we wanted. We wanted a function that returns a function. The only way to do that is to use this syntax or this syntax or this syntax. So Scala gives you all these possibilities. Most people would prefer this because this is the smallest code to write. But I just wanted to make it clear, this is the same. These all three are the same thing, and this is not the same. All right, so let me delete that. And now let's test. So let's call twice on this function. Right, so we apply this function twice to 10. We get 16. Let's see how we can specify types. Well, Scala requires you to specify types somewhere. So you can specify it here. It will then infer that the type argument t on twice must be int. Or you can specify the type argument t on twice. It will then infer that this x must be int. If you don't do that, things won't compile because it won't know that t must be int. Both are the same. So another way of writing it is to write both arguments at once. So twice of this applied to 10. Same answer is 16. Now I'm just testing twice v, which I put over there. Let me just delete this. It's unnecessary to define it twice. Just to see that it gives you the same results, 16. Another syntax for the same as this. Remember in Scala, when you have a function that looks like x goes to x something, then you can replace this entire thing, x to x, by underscore. So that is just making it shorter. Like, this is a function that adds 3 to its argument. So this underscore means argument. This is just fancy syntax. A lot of people like it. So here the tests basically show you all the different ways in which you can write the same thing. Here's another interesting syntax that Scala gives you. Again, it's exactly the same thing. It's twice v, or applying, which is a syntactic variant of twice, applied to the same argument, the function that takes x and goes to x plus 3. However, now I put curly braces around this function, which is possible, acceptable. And note, I don't need parentheses around the type anymore. Now, this is a syntactic convenience. In Scala, in most cases, you want parentheses, round parentheses, for very simple functions, and you want curly braces for complicated functions. Functions in a curly brace can be multi-line. They can introduce new names like vowels. You can do new defs. You can do whatever you want. You cannot do this if you write that in ordinary round parentheses. That just won't work. You are not allowed to have multi-line expressions with vowels and defs inside this kind of parentheses. Scala syntax requires you in this case to write curly brace. Once you write a curly brace, you can have multi-line code with all kinds of stuff in it. So here you can define new things, whatever you want. It can be very complicated. So for this reason, the Scala convention is that if your function is complicated, use curly braces. If your function is extremely simple, use round parentheses. So let me undo all of this and show you. So this is a very simple function that adds 3 to the argument. For such things, Scala provides short syntax. And this syntax is equivalent, but normally used for complicated functions. All right, so much about syntax. So Scala gives you all these syntactic possibilities. No matter how you define the function, the syntax works. So I just have all these tests that check that all combinations of syntax always works. In other programming languages, there are fewer versions of syntax. In Scala, there are quite a lot. I don't think this is a drawback. You can choose the one you like most. The most important thing, however, is the type that always needs to be given when you have functions with fully parametric types. Scala doesn't usually know what x is in an anonymous function expression such as this. The next question is to derive what twice of twice is. What does it do? Well, it's a function, right? Twice returns a function. So when you call twice on something, that returns a function. So what does that function do? So if we reason about this, twice applies its argument 2 times to something. So twice of twice will apply twice 2 times to something. So it will be like twice of something. Now, twice of something is that something applied 2 times. So twice of something means that itself applied 2 times. So now I'm getting already confused. So let's write it down, actually. So these are the various definitions of twice twice. But before we start writing code, let's reason about what it should be. So mathematically, twice of twice is a function that should be applied to some f. So what is that? First we compute this. So twice of something is going to be applying this 2 times to that. So this is the same as twice of f. All right. Now, twice of f is a function. So this entire thing needs to be applied to some x. So this is equal to twice of x going to f of x. Now this twice is going to apply this function 2 times to some argument. In other words, this is some argument, let's say x, and it's going to be applying this function 2 times to this argument. So this is f of x. So that applies the function f 4 times to the argument. Well, makes sense. So these are the tests. If you apply this twice to a function like that, it applies this 4 times, so it adds 12, and so the result, adding 12 to 10 is 22. Now the interesting thing is to apply it 3 times. I leave that to you as an exercise. Apply twice of twice of twice. So I'm going to leave that, and let's concentrate now on types. So we figured out what this function does. It just applies 4 times. How to write it? Well, if we just write twice of twice, things don't work. The way we see that as it doesn't work, if we do Control-Shift-P, that's the type it inferred, and that's no good. It's nothing, 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 so that's no good. That's no good. Now that's better. So the type, why is that type? What is that? So let's reason about the type. So twice has the type which we derived over there. The easiest way of thinking about the type of the function is to write it like this, as a kind of a value with parameter, with no explicit arguments, and just as a value of this type. So this is the type of twice. Now, if I want to apply twice to itself, what does it mean? Well, this is that argument. So the first argument is actually t to t. And in here, it's again the same type. So this cannot be the same t in here and in here, because the first argument of twice is t to t, and twice is this. So the first realization is that these two instances of twice cannot have the same type parameter. So let's call this type parameter A. Let's call this type parameter B. Or let's call this T, just to make it a little easier. All right, so twice T is of this type. Now, what is A? What can it be? Well, the first argument of twice A is of type, so let me repeat this comment and say what is twice a. Well, twice a has this type. It's a function whose first argument is this. The second argument is that. So the first argument of twice a is this. So it has this type. I remind you, by convention, this is how we interpret this syntax with these parentheses. So clearly, this can be a to a only when a is actually t to t. And then a to a is this. All right, so now we figured out that the type parameter a here must be actually t to t. Okay, so what is the result of calling twice with argument twice? Well, we put this in here, so this is twice of a, right? So we put this argument here. The result is this type, so it's a to a. A is this, so it's again that. So a to a is equal to this. Now, this is not Scala code. These are comments that I wrote while I was thinking about the type of this expression. In Scala code, you don't write this. You cannot do that. So you can write that, but you cannot write what I did. So these are just my notes for myself. So now IntelliJ agrees. There are two ways to make, or even three ways, to make IntelliJ infer the types. If I just write this, IntelliJ doesn't infer the type. If I write this, it doesn't infer the type, which I verify here because this example doesn't compile, this example doesn't compile. So three ways that it works in terms of syntax. First, well, obviously we have to specify a type somewhere. First, we specify this parameter, so we specify a. Remember, this was our a. The second is we specify t. The third is we specify the entire thing on the left. Now maybe this is the best way because it serves at the same time as documentation and as code. If somebody reads this code later, it would be very helpful if they don't have to go through this consideration again. This is a calculation, really. What we just did here is a calculation. And I would say it's very nice that we determine things by calculation in our programs. We're not guessing anything. But once this calculation is done, it is nice to document its results so that other people don't have to repeat this calculation again. So, however, all these three things define exactly the same function, which I verify here in the tests. Calling this function, again, requires you, since this function is fully generic, it doesn't have any non-generic parameters, non-parametric types. Generic and parametric is synonymous. It's I prefer to say parametric, but in some programming languages, people use the word generic in terms of generic type, and I say parametric type or type parameters. So when you use this function, you supply anonymous function as the argument. Scala needs to know the type of that function. Either that type is inferred because you specify this, or the type is inferred because you specify this. You can specify both. That's not an error. It's just not necessary. So that's how it works. So now we found out the type of twice. Let's go on. The next example is that we need to take a function with two arguments fix the value of the first argument, and return the function of the remaining one argument. We define this operation as a function with fully parametric types. And here is what we were supposed to do. So we're supposed to have a function, first arg, with 3 type parameters. The first argument is a function from 2 arguments of types x and y to a z value, type z. The second argument of the function is a value of type x, and the result must be a function from y to z. So we fix the value of the first argument of this f. We call f on the x0 and the supplied y. So that results in a new function that takes y as an argument and returns z. So that is the most general type that we could imagine for this kind of function. The code for this function is extremely simple. Just for readability, sometimes I like to put the code of the function on the next line, and also sometimes I like to put this into curly brackets, in the curly braces, just so that it's more readable. This is the code of the function, and this is the type of its return value. But it's just syntax. It's exactly the same thing. If the function is very simple, like this function, for example, it's okay to have it all in one line. All right, so this is it. This is the solution. So how do we reason about this problem? How do we derive this solution? So let me see. If I didn't know how to write this, what would I do? Well, I would write first arg. So we're supposed to have 2 arguments. First is a function of some type x and y, so 2 arguments function. And this is a general type of any function. So it has 2 arguments. Then the general type is xy going to z. I remind you, this is not a tuple of xy. Scala has a distinction. If I wanted a tuple of xy, I would have done this. And that means that the function f takes a single argument that is a tuple of 2 parts having types x and y. But in my problem statement, I was not supposed to do that. I was supposed to define a first arg whose argument is a function of 2 arguments. So that's the general type. And then the value x0 has type x. And then I return. What can I return? Well, there's not much I can return, really. All the types are fully parametric. So I cannot return y, for example, because I don't have any values of type y. I could return x, but that's not what I'm required to do. I'm required to call f, putting x0 in it. So I don't know what that is, but I need to call f of x0 and y should be an argument of this new function. So what is the type of y? Well, obviously it must have type capital Y. There's no other way. So this must be capital Y going to z, because f returns z. So in this way, I'm forced to have this as a return type. And then I need to introduce x, y, z as type variables, since I'm using them here. So in this way, I derive first, well, the code of the function is kind of clear from the problem statement, but then I derive the most general type signature for this function, a fully parametrized function, a type. It does not have any specific types like integer or string or anything. All types are parameters. All right, so that is how I reason about this solution, and then I just check that this works. So for example, I have a function try1 that prints this, and then I fix the first argument, the integer argument of try1 to be 123, and then the result is that. So that works. And also this syntax works. So I can call first arg with two sets of arguments. The first set of arguments having two arguments, the second set of arguments having a single argument. So now, by now, I hope you can understand how this works and how the syntax works. An alternative way of writing this function would be to have a value like, let's just call it first arg1 to make things not break, a value like syntax where this doesn't have parameters, but it equals an expression which is a function. So f, okay, so first I say the type, which is x, y going to z and x. So this is the first set of arguments. Then I have the second set of arguments, which is just y, and then z. And then I say it's f going to y going to, sorry, f comma x0 going to y going to f of x0 y. All right. So this is an alternative syntax for exactly the same function. It has two sets of arguments, which means that here's the first set of arguments, arrow, second set of arguments, arrow, result type. This is a typical thing for curried functions with multiple arrows. And then the first set of arguments actually has two arguments of these types. The first type is this, the second type is this. This is a bit harder to read than that, so I would not prefer to write things this way, but this is equivalent. So it's important that you understand why this is equivalent and how this works. Exactly the same syntax can be used for the second function. Let's run this test to make sure this runs. So this is a solution of this example. Let me just wait until tests finish compiling, and then we'll go on. All right. The next example is we need to implement a function that applies a given function f repeatedly to an initial value x0 until a given condition function returns true. So a hint is that this would be the signature. So we'll have parameter x, type parameter x, and then three arguments. A function from x to x, initial value of type x, and a condition from x to boolean. Now notice we have this boolean, so this is not a fully parametric function. It has a specific logic which is tied to this boolean type. So that's fine. Boolean is a very special type, and that's probably okay. So this function is still widely usable for many different types x. How would we implement this function? So there are two ways of implementing it. If you have gone through the previous tutorial, you have seen how that works. The first way is using iterator, which is a library function. Second is to write explicit recursion. Let me go through the iterator first. I use the iterate function, which is a standard library, parameterized by type x, which is given to me here. And iterate has two sets of arguments. It's a curried function. The first argument is start, which is of type t, which I called x here. You see, x is a type variable. So this is like an argument of a function as well. It's a type argument. So these are value arguments, and this is a type argument. And like any function argument, I can rename this to anything I want. I can rename this to t, I can rename this to blah, I can rename this to anything. So by convention, these are single capital letters, but it doesn't have to be this way. So iterate has the first argument, which is start. Second argument is a function from t to t. So we have exactly the same arguments here. So I give x0 and f as the arguments. So what does iterate do? It creates an iterator that takes x0 as the first value and then applies f repeatedly, getting the next value, and again getting the next value, and so on. That's exactly what we want. However, this will generate an infinite iterator. It will never stop. So what we need is to stop when this condition is true. So we filter, which means we skip all the elements in the iterator sequence for which the condition is not true. After the filter, we still have an iterator of t, but now all elements in this iterator sequence are such that the condition returns true. We actually only need the first one. So let's take one element. The result of this is still an iterator. You see, to see that, I press Command and I hover my mouse over this symbol, and then I see what definition it has, and type and everything. So after this, I have still an iterator of t with just one element in it. So now I can convert this to sequence. The result of that would be sequence of t, having just one element. Then I take head of this sequence, which is just one value. It's safe to take head because, well, either this condition is never true or it's true sometimes. If it's true sometimes, we will get that value. This sequence will be non-empty, and head can be done on a non-empty sequence. If this condition is never true, then this iterator will iterate forever. The filter will be never true, so this entire thing will never return. We cannot do very much about this. Well, we could, in principle, first specify some max number of elements, take that, so we could do this to be safe. Take 1 million elements. But that is not what we were told to do in the problem setting. So in some real situation, we should think about limiting the number of iterations, of course. Let's just forget about this for now. Okay, so this is a reasonably simple implementation. The second implementation uses tail recursion. So that is a direct translation of mathematical induction, which is if the condition is true already on the initial element, that's the base case of the induction, and then we return that initial element. Otherwise, we apply one function f, one time function f to x0, and call the same function again. So we do the inductive step. The value is the same procedure applied to the next value after the initial value. Now this is a little more difficult to reason about, perhaps, than this. And also, what if I wanted to limit the number of iterations? Then I have to complicate this code significantly. So tail recursion is not very nice to maintain. It's, or rather, not tail, just recursion at all. Recursive functions generally take more work to write and more work to maintain. That is to make changes if you want to do other things or make things different. do things differently, it's more difficult to make changes to recursive function than it is to this kind of code, which is on the surface, it's not recursive, it's just calling library functions and working directly on a sequence. So iterator produces a sequence and we just call functions on a sequence. Nothing is recursive here. Recursion is hidden somewhere in the library and it's safe. So it's very easy to change this code to do whatever we want. So I would prefer this implementation in production code. It's easier to maintain. How do I test this? Well, I test this using the procedure to compute approximate square roots with this iteration. So this is known from numerical methods. I iterate a square root sequence. So given x, and if given y, which is an approximation to the square root, then this formula gives a better approximation to the square root of x. And I iterate that with initial value equal to half of x, just randomly kind of chosen. Square root is certainly not equal to x over 2 in most cases, but anyway, that's okay as an initial guess. And then the condition. The condition is that y times y minus x is less than the given precision. So I need to specify the precision. Let me just write it like this to be a little less spaced out. How do I test this? So I say precision is 10 to the minus 8. And then let's compute square root of 25. That should be equal to 5 plus or minus precision. So this is test library that gives me the syntax. And this test passes. Final two worked examples are to infer types in a function. So this is something we have done when we were reasoning about twice, and let's just do this a little more to get practice, to understand how types work on functions. All right, so what is this? So let's reason about this. I already wrote, of course, the solution before, but let's pretend we don't see that. So how do we reason about it? So here's what we need, right? This code is given. What is the type of this value? Well, obviously it's a function. What is the type of the argument of this function? Well, this is some kind of a. So f has type a, and then the code of the function, the expression, is f of 2. Well, that can only work if f is itself a function, and this function has an argument that is an integer. So a must be actually int going to some b. That's the only way that this could make any sense. All right, now what is the result of applying f to 2? The result is of type b. So this will return b. So what is the type of this entire expression? It's a function that takes f, this, and returns this, which is of type b. So it takes, so it returns b, and it takes this as a type. Okay, so it's, let me write it a little more formatted. So this is the actual type. Now, it has an unknown type b, which is not fixed by the code. It could be any type. So therefore, we need this b as a type parameter here. This is how we derive the type. Now, I wrote this solution exactly the same code, except I used t instead of b. So as we know, this is a type variable, so it can be renamed. As we know in mathematics, function arguments can be renamed. Type arguments are a kind of function arguments as well, although they are of different sort. So it's the same if we write B or T or any other letter. So in this way, we infer the missing types. So let's find out if this works. So how do we test? Well, we need to supply a function of type int to t. So let's say t is Boolean. So let's supply this function, which is defined as this. Again, this is a function I used before, which checks that x is even. X going to this expression, which is true only when x is even. So then p of f should equal true because 2 is even. So the function p applies f to a fixed argument, which is 2, fixed value, which is 2. So then p of f is true because f in our example is checking whether its argument is even. Another question here is whether p of p works. And I have a test here that says it does not compile. So why does p of p not compile? Let's reason about the type of p of p. So p of p. Let's write out the type arguments. Well, it could be different type arguments, correct? We don't know that. So it could be different type arguments since they're not written in this expression. Could we find any type arguments a and b that would make this expression well typed? Let's reason about this. Let's replace the expression p of b with its type. Just for our own notes. This is not going to be Scala code, it's going to be our reasoning, which is some mathematical-like notation. So we replace this with the type. So the type of p of b is this. Int going to b going to b. And p of a is int going to a going to a. So this type is a function which is applied to this type. Now, the only way this can work is when the type of the argument of this function is the same as the type of the expression that we're applying it to. So can it be that int going to a is the same as int going to b to b? So the left-hand side is something going to something, a function type, mapping int to a. The right-hand side is again something going to something. So the only way this can work is if a is the same as b here. So, but now it doesn't work because int is not the same type as int going to a. For no possible type a, we could have int equal to this, because this is a function type and this is not a function type. So there are no more type variables. There's nothing we can do to make this match. So for this reason, there are no possibilities to find types or type parameters in this expression so that the types match. The compiler finds this and gives us an error. So if I write something like this, I will have red. Type mismatch. Cannot resolve reference p with such signature. So it tries to find values of type parameters that would match, but it can't. And so it gives me red right away. Now this red is different from the red I would get if I omitted type parameters somewhere. because actually this can never work. Whatever type parameters you put in, it just will never match because of what we just saw. We just saw int cannot be equal to int2a. So that's why it will not compile. The final worked example is this. Infer types in this code and ask questions about Q of Q and Q of Q of Q. So this is kind of a puzzle a bit. So let's go through this just as an illustration of type-directed reasoning. So Q is given as, so let's again start reasoning. Q is given as f going to g of f. F going to g of f. So this is the code that we're given. We should be able to put types on it. So let me put this into braces and let's put types. So f is some type A, maybe. G is of some type B. I don't know what types. So right now I just put some arbitrary type variables. Okay, now g of f is in the code. So it means g must be a function such that its first argument is of type A. So this b must be of type A going to some c. So let's put it more explicitly. Let me remove that because it's not helping. So we assumed f is of type A, therefore g must be of type A to something. So let's call that something c without loss of generality. The result is of type C, therefore. So this whole thing is of type A going to A to C going to C. So the first argument is A, the second is, well, it's a curried function, so it's the syntax with something, arrow, something, arrow, something, where the parentheses around the last pair are assumed. So I'm not going to write them, but these parentheses are assumed. And therefore, the type of Q must be this. And that's the most general type. I have not assumed anything about any types. So for example, G is a function. It must be a function because it's applied to F. But the result of G is any type C. It could be any complicated type. It could be itself a function. I don't care. So Q must have two type parameters, A and C, therefore. And that is the solution. So this is exactly what I wrote here, except I used letters F and T instead of A and C. And I have two versions of syntax. First is when I specify the types on the right-hand side. The second, if I specify the types on the left-hand side. Other than that, it's exactly the same thing. So Scala would not work if I don't specify types. It cannot infer type parameters. So I have to specify type parameters, and I have to specify either this or this. If I specify this, it will infer the right type. If I specify that, it will infer types of F and type of G. I prefer the second form because it shows what type this value is. So this computation doesn't have to be repeated by people who will look at this code later. And actually, I would even prefer Q1, let's say, which has two sets of arguments. One is f of type f, one is g of type f going to t, and that's of type t. So I would actually prefer to write code like this, because that is easier to read. I clearly show there are two groups of arguments, two sets of arguments. Well, these are not actually mathematical sets, these are sequences of arguments, because arguments are ordered here. So first and second, and I clearly separate them, which is easier to read. The types are given, the result type is given, and the code is shorter. So I don't have this longer expression, which is somewhat more difficult to read, and I don't have this expression. However, it's nice to understand that this is actually the function value I'm working with. All right, so when I use this Q, I need to specify type parameters, f and t. Otherwise, it doesn't know what to do and things don't work well, as we have seen before. So let me just emphasize two things. First, these three syntactic forms define exactly equivalent code. There's no difference between the code, except the syntax. Second thing I'd like to emphasize is that this function exists once in the code, and it can be used many times, specifying different type parameters. So I could use it in this place in the code with these type parameters, at another place in the code with different type parameters. I don't have to repeat the definition of this function. And it's not duplicated, it's called with different types. So really, type parameters are like arguments, where you call this function many times with different arguments. You can call this function many times also with different type parameters and different arguments. Here I show different ways of using it. So A has the type int to Boolean, and then I use it on a function which is int to Boolean, I get Boolean. Now, if I don't specify types, then this doesn't work. I have to specify types. Here, it works because I specified that this is returning Boolean. So it could get both type parameters. So you see, sometimes you have to specify types. At other times, if you give both arguments at once, then this is fine. You don't have to specify types. It's never an error to specify type parameters. Just makes your code longer. So it knows this is an int because this is an int, and then that is a Boolean, so it knows this is a Boolean. So in this case, you didn't have to specify this in here, but you could. And if you do, the error message would probably be easier to understand. So if I put here, for example, 10.0, type mismatch, expected int, actual double. But why does it expect int? It's because of this int that I wrote. If I didn't write this, this error wouldn't be noticed. So it's never a mistake to write types. It's safer. It guards against mistakes in the code earlier, but it's just more typing. So it's not always necessary. All right, now what is Q of Q? Well, that's an interesting thing, Q of Q. And you see things are getting very long, very easily. I will not go through Q of Q of Q, perhaps, because it's very similar. So let us go through Q of Q. So let's reason about it. So what is Q of Q? Well, first of all, we need to put type parameters. Q has two type parameters, so it's A and B, and this is C and D, right? Because the two instances of Q could have completely different type parameters. The Scala compiler will try to find combinations of type parameters that work together. It may fail, or it may succeed. Let's see if this succeeds. Just as I did before, I'm going to replace this expression with its type, just for the purposes of reasoning. So what is the type? The easiest way to see the type is to look at this syntax. So this is the type. ft is f to t, t. So this is going to be c, going to c to d, going to d. And this is, I'm just going to copy this in here and replace C and D with A and B. So now I'm going to try to fit the types together. This function has the first argument, which is of type A, and it's applied to this expression of this type. So the only way this can work if A equals this. That's already something. But once that is so, once A is equal to this, then there's no more constraints. So this argument has been substituted. It has the right type. B is not fixed, so B can be anything. So actually we have three arbitrary type parameters now, B, C, and D. Now I can rename them, but I have three type parameters. So QQ, which is Q of Q, has this type, which is applying Q to this expression, and the result is this type. Now A is equal to that. So I thought it updated just recently, didn't it? So let me copy this. And instead of A, let me copy this. Now I need parentheses around it. Let me do it slower. Put parentheses and then copy it in there. Now there are no mistakes. So this is actually the type of Q of Q. It's a complicated type. It's a higher order function, a function that takes as its first argument this function, that takes as its first argument this function, that takes as its first argument this of type C, and the second argument this. So it's a complicated matching of types that will all be performed automatically by the Scala compiler. So the way that Scala can do it for you is first you write this. So we have just figured out that A must be equal to this, so let's put that in the type parameters. And then put all the type parameters explicitly, and then say option enter and add type annotation. So the Scala compiler will infer this type correctly. And in the same way, reasoning about Q of Q of Q gives you this set of type parameters. And so I'm not going to go through this, but you're encouraged to try. Now, something that doesn't work is this. Now, see, there's a difference between this and this. Here, I take Q of Q, and I apply q to the result. Here I take q of q and apply that again. This does not compile because Scala cannot infer the correct type arguments for these two q's. So I can put arbitrary a and b, but it's complicated. So how do we reason about this? It is not clear, actually, at the beginning, whether this expression can be typed. So in programming languages such as OCaml and Haskell, I'm pretty sure this would be done by the compiler because their type systems are different, and these examples can be typed automatically. But in Scala, this is not automatic. So let's reason about it, and this is also a good exercise. So what is this expression? It's the same as QQ applied to Q. Here we have a type of QQ with 3 type arguments, so let's put it here. And this Q has 2 type arguments, so let's take this expression. So basically, our question is, can we find A, B, C, F, and T so that this is a well-typed expression? Now, expression is well-typed when all functions receive arguments of the correct types. That's basically the definition. Here we have this function, which is applied to this argument of this type. So the only condition is whether this function QQ of types A, B, C has the first argument which can be matched with this type. Let's check. What is the type of QQ of ABC? It is this. This is a function whose first argument is this parentheses. So let's copy that. So this must equal this. If that can be matched with some choice of A, B, C, F, T, then we're done. There are no other problems. How can this be matched? So again, the only way that this can be matched is when the left is a function of some x to some y, and the right also is a function from some x to some y, the same x and y. Now, the left is a function from this to C. The right is a function from F to this. Remember, implicitly there are these parentheses here. Therefore, F must equal this, and C must equal this. Okay, can we do this? Of course we can. F can be equal to this, and once that is true, C must be equal to that. So let's put parentheses here and then paste it in. All right. So now we can put this instead of F in here. So let's write code actually. Some parameters B, C, I don't know, T, whatever. Well, actually, C will be equal to that. So A, B, and T will remain. And then we get QQ of A, B, C of Q of F, T. Right? And now let's paste. So F is equal to this. And and C is equal to that. And now everything is green. So now we can do Option Enter here, and it will infer the type. So the type of this expression is actually this, which is the same as the type of QQ, up to changing C to T. So we can rename this to C, and it will be exactly the same type. So this is very interesting. We have Q of Q of this type, and Q of Q of Q is again of this type. So clearly we can continue doing this Q of Q of Q of Q of Q, and it will still have the same type up to some complicated substitutions in the types. Now, this example, I admit, is quite artificial, but this serves to show you how type reasoning works. Here are some exercises for you, and you can apply the typed reasoning as I just showed you in the same way, and I encourage you to do these exercises.